Welcome to the Clima podcast. In this episode, we talk to Barry Cope, the Group Managing Director of ATTMA, the Airtightness Testing and Measurement Association. So let's learn some more about airtightness testing. Clima inspires and educates people to create healthy, durable and energy-efficient buildings to live, learn, work and play in. Awesome, Barry. Well, welcome to the Clima podcast. How are you doing over there?
I'm great, thank you. Thanks for getting out of bed super early to do the podcast with me. It's much appreciated.
Awesome, Barry. No, it's great to catch up. It's a while since I saw you last. Now, I see you're based in High Wycombe, is it?
Yeah, High Wycombe, England, the other side of the world.
Yeah. My aunt and uncle used to live in High Wycombe, so I've been there before. It's a beautiful place.
It's one of those towns that sometimes has a bit of a bad reputation, but if you take it on the surface, it's a town in a big valley in an area of outstanding natural beauty, which is a government-declared zone that stops you building any houses. And it is a really, really nice place.
I do remember visiting there. Now, Barry, perhaps if you can give the audience a bit of an introduction of how you managed to get into airtightness testing.
Yeah, maybe how airtightness took me around the world. My background is that I left school. I didn't do particularly well in school. I didn't do very well in my exams. It's actually exam season here, so it's a good story for those that think they're going to struggle. But I didn't do very well, and I left school and I decided I really needed to do something to try and turn my life around. So I went to study engineering, and I was actually one of the last classes to study what I call old school engineering, which is milling and turning and metalwork and threads and really old school making stuff. And even as I was going through my training, that all of the machines were coming in and the computer aided design, and it just wasn't the same even by the end of my apprenticeship. So I did an apprenticeship. I worked for a brilliant company called Oxford Instruments, and I loved my time there. But when it got to the end of my apprenticeship, they just didn't have a job for me. So they did, but it wasn't something I wanted to do. I always wanted to be a field engineer for them. I had a dream to travel the world, and their field engineers would travel all over the world, quite literally. So I couldn't get a job there. I wasn't experienced enough. I was still a youngster. So I applied to be a field engineer in this new thing for a research company called Tightness Testing. The company was the Timber Research and Development Association, and they had been doing a little bit of experimenting in airtightness testing. It's been kicking around a while. And as I arrived, it had become part of the building regulations. It was in the building code. And I was very fortunate to be kind of young, hungry, and in the right place at the right time, where airtightness testing just became bigger and bigger and bigger. And in the end, I took over the team there, or run the team. And we were, at the point in time, one of the biggest air testing companies in the UK. I think I was 22 years old and was running the department. So it was a great bit of experience. And naturally, I added on acoustics. So I went and studied acoustics in my time. I did my diploma in acoustics and noise control, which I absolutely loved. And eventually my time with that company came to an end. I wasn't fired. I decided to leave and chase my acoustic dream. And I was with another company as a technical manager for about 9 months or so. And ATTMA, who the Airtightness Testing and Measurement Association, had been around since 2001, I think. They had become what we would call over this side of the world a government authorized competent person scheme, which basically meant you were trusted and listed in the building code to run a certification program, or a certification scheme, we would say here. The word scheme has some connotations in parts of the world, as I found out, so I try and say certification program. And I was 9 months into the company. I was really, really enjoying the company I was working for. We were doing great things there. And I decided to take a leap of faith and become the certification program manager for the Airtightness Testing and Measurement Association. And that was in 2014. So I'm now 10 years with them. And we went from it being me with my own laptop, my own mobile phone, in my own bedroom, in a 1-bedroom apartment, convincing all of our members, many of them are still around today, convincing them to join us and to see my vision and how we could help. And we were successful. So We created the ATTMA lodgement system. I'm sure we'll get into that in time to come. But in 2018, 2019, that was the last proper check we could do. About 86% of all of the air tightness testing that happened in the UK was coming through our certification program. We work with the government, we work with lots of different organizations, and we became the first country in the world to have 100% blower door testing in every single individual apartment, every single house in the country. So that's the kind of air tightness testing background. And from that, we set up an organization called CITMA, the Sound Insulation Testing and Measurement Association, which is effectively a mirror of what the air tightness world does for sound testing. And we're now the biggest sound testing certification program, I think, in the world. I'm yet to be corrected. And we also built the Building Performance Hub. And those of you that know both will know the Building Performance Hub was highly inspired by the Clima Hub, as it was back then. So one of the... with ATTMA and with the Air Tightness Testing and Measurement Association, I got to fly around the world. I got to go to the Middle East. We have an office in Melbourne, Australia. It used to be in Sydney. We operate our certification program for New Zealand as well. So I got to travel there, and one of the coolest places I'd ever seen was the Clima Hub. I decided on the day, as soon as I seen it, we need one of these in the UK. Clima at the time were using it for pretty much for membrane install training. And I'd seen it and said, we could use this for air tightness training. We could use this for acoustics training. And instead of having this rig, I could swap it out for a ventilation rig. And it was very much inspired. I spoke to Thomas van Ramstonk, and he gave me his blessing. And for those of you that do know, there'll be a few of you that do know, we employed an outside company to come up with a logo, and they used the Clima Hub logo, the exact same logo, which was highly embarrassing, but very fortunately, Clima had changed the Clima Hub branding to be the cube.
Yes.
And had changed the logo to stop me having to spend thousands and thousands of pounds changing the branding and being sued by Clima, which Thomas assures me he would never do. But yeah, that was almost a faux pas. So we stuck with it. So yeah, long and short, air tightness became my life. Acoustics became my life. Ventilation has become my life. And I've been very fortunate to travel around the world and take these certification programs, even now to America, to the United States. We have members in all across Europe, and we exist for the right reasons. That's the most important thing. We exist as a not-for-profit. We don't take big salaries, I can very much assure you. Everything we do, every bit of surplus funds we make, we reinvest into the certification programs so that we can make apps, for example. We can make our lodgement system faster. We can add new features as Sean Maxwell and ATTMA Australia and New Zealand have benefited from. We've created huge custom features just for the guys out in New Zealand and out in Australia that are doing blower door, so we can keep investing and keep the tools working. But we need you guys to do a little bit more blower door testing, if I'm honest. You guys are behind the curve. We need to make that happen. We need to figure out how we can do that.
Oh, totally.
That's my monologue of an introduction.
Oh, thank you, Barry. That was fantastic to get your whole history there. Awesome. Now, just to sort of explain to the audience, can you just go back a step and explain to them exactly what is blower door testing?
We typically call it air tightness testing here, sometimes called air leakage testing. Those three things mean different things. They're often used interchangeably, but fundamentally we put a fan just like you would have on your desk, like a desk fan, just a bigger version of that. We put that in the doorway or a window of your house, and we pressurize your house. And that sounds quite scary, but what we actually do is blow a very small amount of air into the house, which is kind of like the equivalent of blowing on the back of your hand. And by pressurizing the house, by pushing air into the house, the fans that we use are highly calibrated. We know exactly what's the best word to describe it? We know how much air is coming in through the fan, and therefore we know how much air is leaving the house. The leakier a house is, the more energy use that house will have. Let me give you a classic example. It's like blowing up a balloon with lots of holes in it. That's exactly how our houses are built right now. We have lots of gaps, lots of cracks, lots of leakage paths. Sometimes they're for good intentions, sometimes they're just bad intentions, and never deliberate, but just things that we could do better detailing, holes that find their way into attic spaces and find their way out. So blower door testing is a measure of effectively a measure of energy efficiency, but it's not quite as simple as that. I'm always cautious to tell people that putting a fan in a door and blowing air around is directly related to the energy use of the building, because it's not. It's quite a lot more complicated. We can go into those depths if you really want to go into those depths. Let's try and keep the podcast audience listening. The amount of air that goes into the building is equal to the amount of air that comes out the building. And the blower door allows you to also see and feel where those air leaks are. So we can use lots of fancy tools like theatrical smoke, and we can follow those air paths out and we can seal them. We're probably one of the very big success stories of ATTMA was in 2011, I think it was. We paid the British research establishment, kind of like your CSIRO, similar ilk, to do a report. And that report was to look at 2 different houses that were exactly the same in every way, shape or form. And the only thing different from these 2 houses was 2 different air tightnesses. So the metric we use is meters cubed per hour. So we had one at 15 meters cubed per hour per meter squared of surface area. We can dig into that. And we had one at 5. So 15 is what we would call a typical building in the UK, an average existing building. We have some data for New Zealand to suggest they're not far off. Somewhere between 12 and 15 is the norm for an existing building. If you take that down to a 5, the actual result of that test was that there was a 35% increase in energy that was required to heat that home through a British winter period. And I know our British winters, we moan about it a lot as part of our culture, the British winter. It's not too dissimilar to the New Zealand winter, and particularly the South Island. We're not far off. So those results would still stand. A 35% saving in energy required to heat that same space when there are no other factors. It is by far the cheapest, pound for pound, the cheapest way of saving energy in your home, simply by blocking up the leaks. And we can also talk about ventilation. That's a whole nother story. Air tightness and ventilation are 2 very different things, but are intrinsically linked. If you make your house super airtight, you also need to ventilate your home. Big part of the problem we have, and the question I get asked a lot, is if I make my home airtight, then I'm going to get mold and I'm going to get damp because I'm not ventilating my property. And my argument for that is, by having big holes in your building, that's not ventilating your property either. If the wind doesn't blow, if there's not a big temperature difference, if you're in we'd call a bungalow or a single-story dwelling, you have very little stack effect to pull and move air around buildings. Large holes in buildings are not ventilation. That's just poor design, poor leakage. We can control our ventilation through controlled sources like mechanical ventilation. If we're building a nice airtight home, they're not expensive to put in mechanical vents. We just need to move away from that. I've been arguing with people around the world for the last 10 years about airtight homes being underventilated, and there is no such thing as a home that is too airtight. There is only a home that's underventilated. Otherwise, Passive House wouldn't exist, right? Otherwise, Clima would, I'm not saying most of your market is Passive House, but I would imagine a chunk of your prime market is Passive House, given the quality of the stuff you make. So you need that nice low air tightness. That's a fundamental part of Passive House.
So we've talked about the levels of air tightness in existing buildings. If a designer was designing a new building, what would an appropriate level of air tightness be that they should require from the builder?
I like this question because the appropriate amount of air tightness is none, right? You shouldn't design in or want to have any air leakage in your home, because any air leakage is heat loss or cold loss if you're air conditioning your property. The answer is your design target should be 0. You should try and do your very best to have no air leakage. We shouldn't try and design our homes to a target, or if it says in the building code, you should try and get less than 8 or less than 5. That's not the mentality that we should be promoting. We should be promoting 0. And if you get some air leakage, that's a shame. I would flip the question on its head and say, well, would you want to design in a target to achieve when we should be trying to design in 0 air leakage?
When a blower door tester comes along to perform a test, what are some of the things that they might look at and things that they need to prepare before they actually run the test in that building?
It's actually quite straightforward. The hardest part of a blower door test is actually the surface area calculation. So when we do the calculation, the metric we use to report is air leakage, which we normally would say meters cubed per hour, or if you're America, you'd say cubic feet per minute. So you'll have your meters cubed per hour divided by the surface area of your building. Some people use volume, so you can have meters cubed divided by a volume. But actually, we typically say meters cubed per hour per meter squared is the metric, which you don't need to worry too much about. But, you can't see us right now. If you stretch your hands out wide, stretch your hands tall, and take one big step forward, that's about a meter cubed of air. Even in what we would call a reasonably good home, you'll lose 3 of those every hour for every square meter of surface area of your home. So that's the floor, the walls, and the ceiling. So even in what we would call a very good home, there's still a lot of air. So we would lose a lot of that. So having that calculation done correctly is really very important. We spend a lot of time measuring up because we need to. We would look for the size of the building. So the bigger the home, the more fan power we might need. Now, we're quite blessed in the UK. We have got to a point in our building code for new builds, we can use mini fans. We can use tiny fans. They typically the Energy Conservatory Duct Blaster or the Retrotec 300, 400 series. They're small fans. They're no bigger than a computer screen in height, and they're maybe 30 centimeters in depth. They don't weigh very much. We don't need much fan power to test an airtight building. But fan power is important. If you're testing a warehouse, for example, you may need 10 or 12 fans. You may need lots and lots of air, surprisingly more air than you believe that you ever would. So we're thinking of the size of the building. We have a couple of different ways to test, and it catches people out sometimes. We have method 1 and method 2 in our standards. Method 2, I'll start with, is testing the building in situ or testing the building fabric. And when we test the building fabric, we actually close over and tape over any ventilation outputs, any designed ventilation, because we're only testing the building fabric. When we're testing in method 1, we're testing the building in situ. So we don't cover off. There's a rule that if you can close it, but if you can't, it's just a hole. So if you think of your mechanical fan in your bathroom, that's just a hole. See when that's not on? That may be a 100, 125 or 150 mil hole straight through the side of your building. If I put that hole in your window, if I kicked a football through your window in your main living room, other than the glass, you would say, hey, that's cold. You've got to do something about that. We need to replace the glass. There's a huge amount of air coming in. We have those in our bathroom. And we say, don't worry, it's ventilation. It's okay, right? It's got a fan. But actually, when the fan's not running, it's just a hole. It's letting out all of the nice warmth from your bathroom. So we're looking at that as well. And that's pretty much it. We go in and we blow some air around and we look for, most importantly, the leakage paths. Where's that air going is an important question.
Now, Barry, you mentioned earlier theatrical smoke as one of the methods for finding the leaks. Are there any other methods that you could use?
Yeah, so theatrical smoke is great. It's one of the best reasons for using theatrical smoke is you can picture it. You can take a photograph of the smoke leaving. Most of the time, the best tool that we have is simply our hands. Because if you have air, instead of blowing air out of the building, you suck air into the building. So you turn the fan around and depressurize. You can actually just walk around and feel where the air comes in. Particularly if it's a cold day outside, it's even better. Your hands are sensitive to that cold. So you'll feel those cold drafts coming in. You don't need to spend any money. There'll be some people listening to this podcast right now that say, hey, I don't need a blower door fan. I can feel that cold air coming in. That's not good. That's that's not an airtight home. So just using your hands is the main one. The other one we would find is thermal imaging. Thermal imaging is great at showing leaks. And again, it's great for taking pictures. So taking pictures is really important. Generally, we need to show people where those leaks are, especially if they won't believe us. Thermal imaging requires a bit of a temperature difference inside to out. So you need typically 10 degrees Celsius for the pictures to really show where the air leaks are. But that's for your average home, that's it. For a commercial building, a block of offices or a warehouse, we just use bigger smoke machines. We just blast those smoke machines out and we fill a building with smoke, which often gets the fire brigade called. It's not uncommon here for the fire brigade to rush out to a construction site because somebody's reported smoke billowing from one of the windows. We try and warn the fire brigade, but it's incredibly difficult to warn the fire brigade. If you tell the fire brigade, hey, I'm going to make it look like a building's burning and I do not want the fire brigade to attend, in the fire brigade's mind, they just say, that sounds like somebody's going to set a building on fire and try and delay us attending. So we're going to attend even faster, which is often good fun. So that's the three main tools we use. But the back of our hand is the one that we use on a daily basis here. I guarantee maybe somewhere between 50 and 75% of all the testing that's done in the UK, a tester will walk around and use their bare hands to feel leakage paths, just so they can get a feel for where it's coming from.
What are some of the common mistakes people may make when testing a building?
The surface area calc is easily the biggest. So when we conduct audits on testers, the surface area calc is easily and by far the hardest thing to do and naturally the biggest mistake. You can make a mistake with tubing and not having your tubing set in the right directions. You cannot be competent to test certain size buildings. So we, in the Air Tightness Testing and Measurement Association program, we have level 1 and level 2 testers, and a level 1 is typically your domestic tester, would test your houses, and level 2 would test big buildings, multi-fan stuff. And that's because we have to be very careful about air paths, making sure we evenly distribute pressure around a big building. So it's very easy to think that you're pressurizing a large building, but actually if you haven't got your tubes in the right place, if you haven't got your building set out right, if you haven't got your fans distributed around, you can not quite get the pressure. Granted, that's a lot rare, but generally there's not many mistakes you can make other than just standard human error, putting the temperature with a decimal place in the wrong place. We get that sometimes. Actually, one of the biggest isn't even about testing, it's just making a typo in the address. One of the biggest we actually see, thinking about it, typo in the address, or misspelling the country. I think on the last look that I had, we had 19 different spellings of England.
No.
I think it only has, 7 letters? We have 19 different spellings. So we're forever coding things to try and pick those errors up and speak to the people to say, in the best of, in the kindest of ways, you need to spell England with an E, not an I.
So, Barry, people might be listening and thinking, how could they actually become a blower door tester?
It's pretty straightforward. It's almost a business in a box. It's one of the very few industries where you can go and sit a training course, which is typically 3 or 4 days. And I think you can do it modular in Australia and New Zealand. You can sit that exam, sit the theory and practical assessments, and then you basically submit 3 unpaid tests, we call them, which sounds harsh, but you go and test your house and your brother's house and your auntie's house, maybe your grandma's house and your nephew's, niece's, son's, brother-in-law's house, and submit those to ATTMA. And once we're happy that you know what you're doing, then we will push those on to and invite you to apply for certification. You need to buy the equipment, of course, which is a good few $1,000s, but you can earn good money doing blower door. And the market is definitely on the up, particularly in Australia, particularly in New Zealand. We've done, and I say we, I mean Shaw Maxwell has done a huge job in pushing the blower door market in Australia and New Zealand to really make sure it gets put into the building codes, and is something we do a lot more of because the buildings are leaky. We need to make improvements of that. So effectively a training course, buy the kit, pay your fees, get some insurance, and you can get out. I think the quickest turnaround we ever had was something like a week. So 3 days of training. They already had their kit. They go and do some unpaid tests, submit them to us, we check them, and by Monday you have your license to go and do testing. You just need to win the customers.
So just to go back a little bit, you talked earlier about the fact that the UK obviously is testing every single building, new building. Now, what was that like in the beginning when the government first required that? It must have been quite a scramble to get all the testers trained and people out. Can you give us a bit of a feedback? Because it'd be interesting to know what we can prepare for.
Yeah, you'd actually think it was a big scramble, but it really wasn't. And that's just because of the way the building codes are released. So if a building code here changes, or it changes in New Zealand, you typically get 6 months notice So the document will drop and it will say this document is effective as of 6 months' time. And at that point, it's only effective for buildings that go through the planning process. There's normally a handover period from if you applied and started using the old building code, it was unfair of them to apply the new building code onto you halfway through a project. Because over here, that could include changing an energy model, that could include substantial changes to a building, structural changes that just mean you would never complete the building. So it was actually the opposite. I want to say we, there's the kind of the people I refer to as the originals, the people that were out doing it in the very early days. We made a fortune, dude. Yeah, well, I didn't. It was from my employer, but we made great money because it was a very simple supply and demand. No one really knew about it. We were doing it. There was very few people doing it. And the more and more that it became a requirement for those new homes, the more people trained. But actually, it wasn't as scramble as you think it might be. Between the building regulation being printed and that being official and doing the first blower door test for regulation purposes was something like 2.5 years. It was a really long time because it just required them to finish their current housing, start the new housing. That could be months and months and months planning and everything before they get to the completion, because you typically do a blower door test as one of the last jobs on a project. Unless you're working, you might do a test at membrane stage to check your membranes are nice and airtight, which is highly advised. But in the UK, typically you're in the building with the cleaners. That's how late you are. There's quite the gap. So that allowed a lot of the industry to train, that allowed the industry to settle, organize itself. And what's really cool about Australia and New Zealand is we've actually learned from what we've done here in the UK, and we've already made that happen in Australia and New Zealand. We already have the people, the organization, the lodgement system, the insurances, we have the technical support. It's all exists before the regulation changes. And we're just waiting the day. It's when, not if, that it will change in New Zealand, and when, not if, it will change in Australia for a good chunk of the climate zones.
Yes, of course. Now, just to sort of look further afield, what do you see developing around the world in the way of air tightness requirements?
I just think it will become a lot more normal. There's two things. I think blower door testing is like any industry. We never pretend that blower door testing is the perfect solution, but thousands of these tests are done in the US every day. We know in the UK it's probably closer to 500 tests a day are being done. There's whole companies that employ tens and tens of people whose full-time job it is to go to different construction sites every day and keep testing. So we're going to do more testing. Countries like New Zealand, it's coming because it is, as I said at the very beginning of this, one of the most cost-effective ways of reducing energy usage in your buildings. You can make even a 20% reduction in the amount of energy you use. That adds up over 10 years. That's a lot of money. So it's just going to come to more and more countries. More and more countries will get to 100%. And my best guess is that as we start hitting our targets, we get to 100% compliance. We'll do less and less. We'll go back down to sampling. So with New Zealand, Australia, the Middle East, the US, these countries are doing samples of construction sites and realizing they start needing to do all of them. We're at the top of that list. We're going to start going the other way. I say to building contractors all the time, if you built in an airtight manner, airtightness testing wouldn't be a thing because we wouldn't need to be here. If you take the colder Nordic countries, for example, Sweden, Norway, they don't do much blower door testing. The reason is they know about it if they build a bad home. If you look at Alaska don't do much blower door testing because they know about it if you build a hole in a house. So we'll get to that point where we'll get to 100%. The other thing I think that will happen is in the UK, we have energy performance certificates. So that we have our energy model. As part of that energy model, you have to do some on-site verifications. One of those is air tightness testing. And you are produced a piece of paper with a rainbow graph on it, just like you might get on your washer dryer. And it says your energy usage. So you can be categories A to F, I think. I think you have to be D or something to build now. The predictive model, the predictive way of working is going to go, and we're going to be using actual energy usage as our metric for how energy efficient a home is. So there's lots of companies out there that are developing overnight heating tests. You heat your building up. At midnight, you turn the heaters off, or they go off automatically, and you judge the cool down time of that house, how long it takes to reach the ambient temperature outside. Theoretically, if your house is nice and efficient, that's going to take a long time. And if your house is really inefficient, that's going to happen super quickly. And that's going to be how we judge our energy usage in buildings. We're not going to make a guess and say, we think there's a few holes and there might be some gaps around the windows and we think there's 150 mil of insulation. We're not sure. Has it been installed properly? No idea. And we produce an energy model that isn't particularly efficient. It's going to be actual on-site testing, verified performance to make your home, to get your true energy performance. And I think coming straight off the back of that, I think this is all going to tie into how we borrow money to buy houses. So the government and the banks are going to very quickly realize, or have already quickly realized, the assets that they lend against, need to be high quality. If you have a super energy efficient home that has solar panels, that is airtight, well insulated, and proven to be that way, you know that there's less risk because they're not going to be stung by a high energy bill one day. There's less risk as a lender on those properties. They're being called green mortgages here. So you can only get a green mortgage on a very highly performing home. I think that's going to take off as well. I think mortgage companies are going to not just look at you, they're going to look at the asset they're lending against, and they're going to say, is it energy efficient? Are they going to need to borrow more money to improve it? I think that's really where we're going. The blower door is just the start of this.
Excellent. Just to finish off this interview, Barry, what would you see some of the expected future developments of air tightness coming down the line?
Future developments, I think blower door is super simple. It's a very simple concept. I don't think we need to go and reinvent the wheel when it comes to blower door. I think really the fans will get lighter, they'll get more powerful. The method of blocking off the door or the window will be faster. But fundamentally, we just blow air into buildings or suck air out of buildings. We just need a fan. There are plenty of other technologies that do similar things. So in the UK, we have one here that releases a pulse of air and works at a very low pressure. We'll leave that one there. There's like an infrared, hypersonic, supersonic, not supersonic, high frequency. We'll call it high frequency measurements, where you have a speaker that produces super high frequency and you can effectively measure gaps and cracks in your buildings. There are some downfalls, particularly when it comes to using membranes and convoluted air paths. Air is like water. It will go where it wants to go. That's it. Nothing more, nothing less. So air leaks aren't just holes from direct from one side to the other. Sometimes they might go down and back up somewhere. So there are some flaws with that technology, but they're pushing on really fast. There's thermal imaging. We're getting very good with thermal imaging now, and being able to look at leakage paths with thermal imaging and quantify them. Lots of people working on that technology. I've been doing this since I came out of school. I'm yet to see a solution that's as good as simply putting a fan in a door and blowing air around. That's it. It's all we do. I always describe it as the most simple thing that we do and the most complicated. On the surface, we blow air into a building. We know how much air goes in, so we know how much air goes out. That's what a blower door tester does. In reality, we can talk about N values and flow rates and laminar flow and stack effects and all these wonderful things about how truly the building sciences work. We could talk moisture, humidity, but on the surface of it, we blow air into buildings. And I don't think we need to change that. I don't think we need to reinvent the wheel.
Fantastic, Barry. I really like that. Thank you so much for your time. My morning, your evening, and I'm sure we'll chat again soon.
Absolutely. I'm sure I'll be in New Zealand either later this year or early next year, and we'll catch up for a cold drink. So
sounds great. Thank you, Barry. Sharing knowledge is at the heart of our strategy to make buildings better for everyone. Sign up for our podcasts to learn more about creating healthy living conditions by protecting building structures from external and internal moisture damage. Thanks for listening. Looking forward to having you with us next time.